Welcome to springlib.
Okay, so we've been shown this reaction where we start with an alkyne, and we're going through hydroboration oxidation. Initially, the boration step, the boron is associated with large alkyl groups that won't play into how this reaction proceeds. The important thing is that in the second step, we're shown the following intermediate. And what I want to point out is that if we call this carbon 1, 2, 3, and 4 in that intermediate, then what we end up with is a bond between our previously identified carbon 1 and boron. And that in the final step, when we do the oxidation of our intermediate, the only real difference is that the bond between carbon 1 and the boron group, including all the alkyl, everything is going to be replaced with an OH, right? So we'll just end up with a bond between carbon 1 and OH. Okay, so we can really just draw the same thing, but with a bond to OH, right? Where this is carbon 1, this is carbon 2, this is carbon 3, and this is carbon 4. Now, we're not done here. This is the enol intermediate that they mentioned, and they tell us that this tautomerizes to an aldehyde. And all you need to know to follow this tautomerization is that you'll still have a 4-carbon chain, just like we have here. Right? Let's call this carbon 1, carbon 2, carbon 3, carbon 4. But whereas we used to have a double bond between carbon 1 and 2, we'll now instead have a double bond to oxygen. Okay. In a sense, this hydrogen moves over there, making room for the double bond. You can think of it like there is where that hydrogen is, in a sense, moved over there. But we wouldn't show that in the product. In either case, if you want to show tautomerization between an enol and an aldehyde, that's basically the rule. Get rid of the double bond between the carbons and put the double bond between the carbon and the oxygen instead.